In Part 1, we introduced the idea of combustion as a gas phase reaction that converts fuel to combustion products. The critical concept was that combustion is a gas phase reaction. I am a mechanical engineer, and when I first heard the term heat release rate, I thought that meant specifying the heat flux from a surface, for example from a stovetop. That concept is not correct. Instead, when we specify a heat release rate in a combustion analysis, we are really specifying the rate at which fuel is introduced into the simulation. How is the mass flow rate calculated? In Part 1, we stated that combustion is based on a stoichiometric reaction where all the fuel reacts with air to form combustion products. We showed the general stoichiometric equation, but did not provide details. Here are the detailed equations for a clean methane fire and for a more complex and sooty polyurethane fire. We can perform the stoichiometric calculations in a spreadsheet. For methane, I input the carbon, 1, and hydrogen, 4, content of the fuel. The heat of combustion will be based on the energy per unit mass of oxygen that is reacted. Let us say that I want to calculate the total mass flow rate of methane needed for a 500 kilowatt fire. Solving the chemical equation as described in the FDS user manual gives us the stoichiometric coefficients. We can then calculate the stoichiometric mass fractions, and from that information the mass of oxygen in the reaction. We then see the calculated heat of combustion and the mass of fuel flow needed to release the desired energy. 0.00957 kilograms per second. Let's verify that FDS performs the same calculation. We define the methane reaction. We perform the analysis. After we run FDS, we can open the .out file and find the gas phase reaction information. We see that FDS does match our calculation of stoichiometric coefficients and our calculated heat of combustion. If we plot the results, we see that the mass flow rate matches our expected value of 0.00957 kilograms per second. That defines the fuel used for combustion. The heat release rate plot integrates the actual simulated heat release rate. It is not constant because although fuel is being supplied at a constant rate, turbulence causes fluctuation in the airflow, so the combustion and mixing changes with time. However, we see that the average value of calculated heat release rate corresponds to our specified value of 500 kilowatts. We can repeat this verification for the more complex polyurethane case. The expected mass flow rate of fuel is 0.0252 kilograms per second. The combustion produces large amounts of soot, but we still confirm that the expected fuel flow rate matches our calculation and that the desired heat release rate is being calculated. Specifying the heat release rate determines the mass flow rate of fuel introduced into the simulation. A stoichiometric calculation is used to determine how much energy will be released during combustion and thus the required fuel flow rate. The plotted heat release rate shows the heat release during the actual combustion simulation with all of its complex airflow. In the next video, we will discuss a burn model.